Welcome to the Science Edit, the podcast that breaks down the trickiest parts of science and helps you get it right when it matters most. I'm Miss Lima, and I'm here to support you with the science you need when you need it. Whether you're revising for exams, exploring future careers, or just trying to figure out why your last test didn't go so well, you're in the right place. Let's dive into our next episode. You've revised the topic, you understand the formulae, but the marks still aren't coming in. In this episode, we're digging into the most common pitfalls students face in GCSE Physics. From units to practicals, graphs to calculations, we'll explore where things go wrong and how to stop losing marks on things you do actually know. Today, we have two physics teachers who have 43 years of teaching experience between them. They're joined by a Year 12 physics student who's been through the whole process. We're asking, why do I keep getting it wrong? The physics basics. So thank you so much for joining me today.
You're welcome.
Thank you, Miss.
Happy to be here.
So I guess one of the first things we should be talking about with physics is units and conversion errors that people make.
Yes, indeed. So units and conversion errors. This is something that causes mistakes time and time again. Students really need to get to grips with learning unit prefixes. So what do we mean by milli? And I always talk to my classes about millimeters, as that is very common and easy to understand.
An easy one to kind of link to prior knowledge.
Exactly. Beyond that, students often know about kilobytes, megabytes, gigabytes, and understand that they're a power of 1,000 greater than the previous term. So this is what I would recommend students really get to master, is understanding what the prefixes are and what they mean in terms of a standard form.
Yeah, that's a really good point. I think, especially when you're in an exam, it can be quite rushy. So if you're definitely going through your exam paper and you're in a bit of a rush, sometimes you do miss the unit or the SI unit. So just be really careful to check or double check when you read the question. Is it in millimeters? Is it in milliamps? Is it in microamps? Because if you miss it, you're going to lose out on that final answer mark.
Isn't that also a really good tip with that, is to double check that your answer actually makes sense when you go back and read the question again at the end?
Absolutely. Checking that the answer has gone up or gone down as expected. So if I'm multiplying something by something else greater than 1, I would expect a higher answer. And also checking that you get a value which you expect to get. So if I get a value of 1,000 kilometers for a walking journey, obviously I realize I might have made a mistake with the units or the conversion using the prefixes.
Yeah, actually, I think that's a really good point. So I often find students have given me values which I just look at and go, well, how could it possibly be that? And students are in that high pressure situation, feeling maybe stressed and I've got an answer, let me just write that down and move on to the next question. And I often tell my pupils that actually you really need to slow it down, because quite often pupils will have 5, 10, 15 minutes at the end of an exam where they're sat twiddling their thumbs. And they should be using that time to check their answers. And when they check their answers, they shouldn't just be going, oh yeah, I understood that question, I'm confident I got the right answer. They should be looking at the calculation again. They should be thinking about, does that value make sense for this scenario that I have been given?
And obviously making sure that you include the units in your final answer as well.
Oh, definitely, yes. Make sure you include your units. Without units, it's just a number, and a number has no meaning.
So another area that causes students quite a lot of anxiety are the equations that are included. So what tips do you have about using those?
Well, I'll make a start on this one. So I always recommend to my pupils that if they know that they are not so confident with how to rearrange an equation, they employ this simple technique. So take the equation for Ohm's law, V equals IR. That could be 6 volts equals 3 amps times by 2 ohms. So 6 equals 3 times 2. Every single person I teach knows how to rearrange 6 equals 3 times 2 to be 2 equals 6 divided by 3. So they just use that format to apply to all equations. The only exceptions that won't work for is in slightly more complex equations for, say, kinetic energy, which is half mv squared. So there are a few more terms there. Or with specific heat capacity, that the change in thermal energy is equal to the mass times the specific heat capacity times by the change in temperature, in which case it becomes 24 equals 2 times 3 times 4. Make sure you don't use number 1, because timesing or dividing by 1 gives you the same value.
Well, what about the use of equation triangles? Do you recommend those?
Equation triangles are not awarded credit in exams. I do mark exam papers. My personal viewpoint is use them as working if you have a scrap sheet of paper or if you're using it on the side, but they will not be given any credit. The credit, when we mark an exam, we give credit for substitution, so seeing the numbers in the right place, and a good formula rearrangement would draw your marks. So while they might help you in rough working, and I stress that must be rough working, the working won't draw credit from an examiner, a professional examiner marking your paper.
Yeah, I'd like to add to that. Personally, I'm not a fan of formula triangles, for they are a sort of sticking plaster to the issue. If you're struggling to rearrange an equation, the way to deal with that is to understand how to rearrange equations. And the formula triangles, they're just a sort of little magical bullet that you just cover up one corner and it tells you what the equation is. I think it's far more beneficial to learn how an equation works, that you do whatever operation you do on one side of the equation, you need to do on the other side of the equation to make sure that your equation still remains true and valid.
Yeah, that's a really good point. If we're looking at formula triangles, they are really, really simplistic. So if you're starting to get to those higher level physics problems where you're having to combine equations like a half mv squared and mgh, you're going to have to know how to rearrange to get an exact value. If you're using a triangle and then you start to combine equations together, you're not going to be able to use those triangles anymore. So, yeah, like you said, sir, if we're filling the bullet hole, we're now putting a plaster over a gunshot wound because you're just not able to do that anymore.
Thank you very much. Yeah, really good.
So let's move on to some individual topics. The topic of forces in motion does give students some problems sometimes.
Yes, indeed. I think the key takeaway that I always stress to my pupils is what do forces do? And more importantly, it's the resultant force. It's the concept of resultant force that students often struggle to comprehend. So we all know quite commonly that F equals ma, force equals mass times acceleration, a kind of simplification of Newton's second law. But it's the net force which is equal to the mass times acceleration. And therefore we need to be able to do some vector addition in order to be able to calculate that net force.
I find resultant forces easy to teach because I remind students that the resultant force is the result of all those forces. And in any situation, so if lots of people are pulling on the rope, there will always be one result in a tug of war, for example, or in a stage dive. Obviously, although many audience members might be pushing or pulling in different directions, the performer can only move in one direction, the result of all the movements. And I'll echo your point there. It's very important to know how to add vectors as part of that topic.
Yeah, that's a really good point. In fact, I have actually made this mistake before in one of my mock exams. There was a question to do with springs and the forces on the spring and acceleration, so I used that equation, F equals to ma. But when I looked at the diagram, I forgot to see that there was a resistive force, so that when I was calculating the acceleration, I'd only use the downward force. So I didn't have the resultant force on the spring. I had one of the forces, which led me to lose, I think, all three of the marks.
Ouch, that's a punishing mistake you made there. I think another thing to add on forces is, which is probably quite a simple mark to lose, is just naming the forces correctly. The recent assessment we did with our year 10s, many pupils were unable to label a force tension when the weight was hanging on a string. So I would really recommend that pupils make sure that they are familiar with the different types of forces and name them correctly. One other area which is often incorrect or not accepted by exam boards is to label weight as gravity. You could correctly say gravitational force, but my recommendation is that's lots of letters. You might get confused over spelling, so just use weight.
And force arrows as well. There's particular rules with those, aren't there?
Yes, so when we're adding vectors in a scale diagram, I was just last period talking with some pupils about how to draw scale vector diagrams. And one student made the mistake of drawing all vectors from the same point rather than from tip to tail. So the scenario was an aeroplane was driving with a thrust of several thousand newtons and there was a crosswind at 90 degrees. They drew the vectors from the same point and therefore when they connected the ends of the vectors for the resultant, the direction did not make sense. It should have been going up to the left, but they had it going either up to the right or down to the left.
So one of my least favourite topics is electricity. It can be very confusing to students, can't it?
Yes, electricity is one of those topics that pupils will either melt away and wish never to learn again, or it's a topic which students find fascinating and really want to understand more, but they still find the abstract nature of a topic something that is difficult to get to grips with. So, for example, current, voltage and resistance. It is absolutely vital that you learn the definitions of these terms, even if that means just by rote learning. You need to learn these definitions to apply them to more complex scenarios. So current, the rate of flow of charge, and the rate is a really important aspect of that definition. The potential difference or voltage, the energy transferred per unit charge. How much energy is transferred to a quantity of charge, namely 1 coulomb of charge, which is many, many billions of electrons. And resistance is the ratio of how much potential difference is required to force current to flow at a rate of 1 amp through a component.
I think that's a really important point, actually, to get those definitions down correctly, because in lower school, students often learn that voltage, for example, is a push around a circuit, and so obviously it could be tempting to describe that incorrectly in a GCSE.
I think that's especially important when you're starting to think about the rules of like series and parallel, because if you don't understand what's going on with these three components, then you're going to really struggle to answer these more advanced questions. Like, for example, knowing that the current is shared in series. Well, if you don't understand what current is, or you don't know its definition, it makes it really hard to actually answer these application questions.
I'm just going to cut in there. When you said the current is shared in series, can you just explain what you meant by that?
Okay, fair enough. Am I not specific enough there?
I think you've just highlighted a really key point. So when you say shared, does that mean the same or divided by between the number of components?
Okay. When I say shared, I mean divided between the components.
In series?
In series.
Okay, so we've just got a misconception live on air there. So when you said that the current is shared, it's divided up. Well, if one component leads into another component, where do those missing electrons go, do you think?
You make an excellent point, sir. They're not going anywhere. They're going to travel into the next component. So the current would be the same, would it, sir?
That's exactly right, yeah. So in a series circuit, the current is the same for each component because the number of electrons per second moving past a point is the same at any other point in that series circuit. Otherwise, as we've just said, those electrons must be disappearing into the ether.
A main skill that students have to master is looking at graphs and analysis of data. Any tips on that?
Slow down. I have pupils who have recently just been doing past paper questions where I had to remove marks because they plotted their points more than half a small square. Yes, that's right. Only half a small square of uncertainty is allowed by exam boards. So if you're a whole little square away, you will be penalised a mark for that. And you might think this is easy marks. Well, you've got a minute per mark roughly. So spend that minute to take your time and be sure that to within half a small square, you are plotting correctly.
Another big issue is the line of best fit. People often assume it's a straight line of best fit, and in many situations it's not, it's curved. Now, just because the line of best fit might be a curve, for example, in a radioactivity graph, doesn't mean it shouldn't be smooth. That's a mistake people make. So it's one smooth line of best fit, which could be a straight line or could be a curve.
There is a little bit of controversy here with physics and maths, because maths, the word line, stems from the word linear, which means straight. However, if we only ever experience relationships to be linear, then we would not find that we are modelling the way the world works. It wouldn't fit our data. So we in physics maybe play a bit fast and loose with the word line, and we say that that line can indeed be curved, a curved line. Rather than a definition of line from linear, we're being more colloquial with that use of the word.
That's a great point, sir. In a sense, you could also use kind of your intuition. So if you're looking at the question, and it's a question about radioactivity, and it's told you to draw a decay graph, you're going to think that it's going to be a curve, kind of an exponential decay graph. So if you're drawing this line in and they've given you the data points, from what you've seen in diagrams and tables from lessons, it kind of makes sense to join all the points with a nice curve, because that's how they work.
Thank you, yes, very good. Another issue with graphs, and we've already alluded to this, is unit prefixes. So that y-axis, that x-axis, what is the unit? And crucially, this happens even to my A-level pupils, exam after exam. How many meters or how many amps does that graph really tell you? Is it milliamps? Because that's going to really affect your gradient. So be careful there. Make sure you're always paying attention and looking for those unit prefixes.
I would even go as far to circle them in your exam, because you're going to be stressed out no matter what. They're always, tests are always quite stressful. And if you're going through at a quick pace, you might miss the fact that that wave graph had a period in nanoseconds or microseconds rather than in just seconds. And that, like you said, so will completely change your answer. But if you circle it and you can see that it's clearly there, then you know you're not going to forget about it.
That's a really nice tip.
Yeah, I really like that too. I think, again, like I was saying about slowing down in your exams, using the time you've got available to you, anything which is going to make sure that you're not missing key details, like just getting it into practice now. Whenever you do past paper questions in your revision, formulate the habit that you will circle units, you will circle the labels of your graphs, and get into the habit. You have the time to do it in your exam, so get in the habit now.
Looking at the core practicals specifically, what kind of pitfalls do students often fall into?
Well, the biggest pitfall is the identification of variables, the quantities that you're measuring and setting.
That's not just with physics.
No, well, but especially in physics. It's identifying the independent variable, which is the one that the investigator changes, the dependent variable, which is the one that changes because of the change to the independent variable, and the control variables, which have to be kept constant.
So I often find pupils really struggle to understand why independent variable is the one we change, the investigator changes, and why dependent variable is the one that we measure. And I've explained we are investigating a relationship between two quantities. They both change. One changes independent of that relationship. Therefore, it's only changing because we change it. The one which is changing that depends upon the relationship we're investigating must be the dependent variable.
That's a really nice way of putting it.
One core practical where this is particularly difficult in the GCSE course is the Newton's second law required practical with trolley cars, because in that experiment you can either set the force, the tension, and vary the mass, or you can set the mass and vary the tension. I found that required practical, the one with the trolley cars investigating F equal to ma, should be given a little bit more dedication and revision time when preparing for your exam.
Just a question for both of you physics teachers. So, say I'm a year 11 student and I come across a question that says, how could I improve the accuracy of that experiment with that trolley car? Or just in general, how does a student approach these type of questions?
That's a really good question. How to improve the accuracy of a practical, specifically the F equals ma practical. So where are sources of error? So you're possibly using logic gates. And logic gates actually have a very small source of error because they measure time to a very small degree. You are measuring mass, that you're hanging on a weight as you're accelerating force, and you're using a top-hand balance to measure the mass. I think one thing which is probably the key part which people forget is the control variables and how the control variable plays a role in making sure your results are accurate. So you want to make sure that the trolley mass stays constant. But when you add masses to a hanger over the pulley, you're increasing the mass because that accelerates at the same rate as the trolley. So you need to remove that mass from the trolley and put it onto the hanger. And that is what they're going to be looking for that question. It's not necessarily adapting your equipment or the technique of using the equipment to improve your accuracy in this scenario, but it's more about how are you ensuring that actually the result that you get is valid.
Obviously, we've overlooked quite a big source of inaccuracy, which is human reaction time. So we immediately assume that we're using light gates or logic gates to time the trolley car. An easy win is, if they haven't mentioned what technique they're using, is to recommend the use. And be careful, don't just say logic gates or light gates. Say light gates linked to a processor, computer.
Thank you for that. Yes, that was a little oversight from me not making that clear.
Yeah, because obviously, if you just say light gate or data logger, you won't get the mark unless you have linked it to some sort of processor, laptop, or data.
The same thing can be said for other required practicals, for example, like using a ripple tank and having to determine the frequency. You need like a marker in shot, but you can video it and you can count how many of the shadows or wave fronts pass over that pencil point, but you need to know in what time did that occur. So if you don't make it clear that the stopwatch is also in shot, or that when you play back the video that the time passage is visible to you, then you won't get the credit for accurately determining what the frequency of that wave is.
With that practical, I hear the word frame by frame in the videos being thrown around. Is this a good word to use when describing that improving of accuracy, or should I go another way?
Yes, they do accept frame by frame. So the key point that you're making is that you're viewing the experiment at slow motion. So as long as if you say, look at the experiment on video again, you won't get credit for it. But if you say, use video to view it in slow motion, or use the video to see it frame by frame so that the time can be determined accurately, that's important. Because remember, we're mentioning what we're measuring, which is time. Viewing the video is not really important. What's important is that we get an accurate time. And just to add, the word accurate means true or valid. So if it's not true, it's not accurate. So you're trying to get as close to the truth as you can. That's a good way to think of the word accuracy rather than precision.
Finally, I'm going to put you all on the spot, and I'm going to ask you if you could give one top tip to students that have got their GCSEs coming up in terms of the exam technique. What would you say?
One top tip. Wow. I'm just going to have a little think for a second. I'm thinking that the majority of pupils that I teach in my school are quite comfortable with the mathematical side of things. So it would be to spend a little bit of time thinking about why things occur. So a lot of the difficult questions are, the command word in the question is explain. So describe and explain what the result of X changing will be on Y. And many students are really quite confident with saying what the change will be, but aren't so comfortable with saying why. And that requires a little bit of a deeper understanding about the physics involved. So that requires you putting in that legwork to really be able to work on how you phrase what your understanding is. And the tip there is speak to your teachers. Check that your understanding is correct and that you are able to verbalize your understanding in a way that is grammatically correct and uses the terminology correctly as well.
My tip would be to be very clear in showing your working. People often neglect to show their working, for example, on graph work. When you take a reading off a graph, use a ruler, use a pencil. Feel free to draw the line quite firmly, because examiners will look at working on the graph. They will look at diagrams. As long as the diagram doesn't contradict what is written, they will always prioritize what's written. However, also when you do your working, try your best. I know nerves kick in, but if you can show your working in sequence, left to right, top to bottom, because often an examiner might miss marks that they would have given you simply because you put the start of your working at the bottom and the end result at the top. So I'd say show your working. That's for numbers and for graph work.
Yeah, that's an excellent point, sir. And my final tip for the Year 11s, and maybe not their favourite one, but is definitely to learn the things that will come up in terms of definitions and your required practicals. So a lot of the students are really mathematically capable or are really good at explaining the concepts, but sometimes when they're asked a definition question or to list the entire process of a required practical, they often haven't sat down to think about what to really say. So if you look at the mark schemes, they can be really specific. Like the word you mentioned earlier, current, being the rate of flow of charge. If you miss that word rate in your definition, you're probably not going to get the mark. So my biggest piece of advice, and the Year 11 students will probably hate me for it because it's the most boring, but learn your definitions.
It's important.
It really is important.
Well, thank you so much for joining me today and for the great tips for students. If physics sometimes feels like a subject where you lose marks, even when you kind of get it, you're not alone. Focus on the patterns, sharpen your exam technique, and remember, understanding the content is only part of succeeding. Showing the examiner that you understand it is what really gets the grade. If you have any comments on today's episode or have an idea for a future episode, please send us a message at contact@thescienceedit.com. See you next time.